All right, so now we're gonna be talking about carbohydrates. For this chapter in general and the next chapter on amino acids, there isn't that much content in the space of concepts. A lot of it has to do with just memorizing things. But yeah, let's just get right into it. So these are three example sugars: D-glucose, D-fructose, and D-ribose. So this is something called an aldehyde, right? Whenever we have a carbonyl O with an H, that's an aldehyde. Therefore, we call it an aldo. Six carbons, one, two, three, four, five, six, hexose. Aldohexose. Ketone here, carbonyl O, C, C, six carbons, one, two, three, four, five, six. Keto, hexose. Okay, and as we would expect, aldehyde, five carbons, aldopentose. Cool. So when we classify it, the easiest way and a very common way to classify sugars is by the type of carbonyl and the number of carbons we have, right? So aldotriose, aldotetrose, aldopentose, aldohexose. So whichever carbonyl type we have plus the number of carbons that we have. In terms of number of sugars linked, this is an example of a simple sugar, right? We just have one sugar. We call that a simple carb or a monosaccharide. For complex sugars, we split into three categories. If we have two linked, that's a disaccharide. 3 to 10 is an oligosaccharide. And anything past 10 is a polysaccharide. Okay. D and L notation. So D and L notation are relatively similar to S and R, but not precisely the same. Okay. So it's almost the same for all of them except for one sulfur-containing amino acid. And we might talk about why that is later. But basically, we have this carbon here, this carbonyl carbon here. We look at the bottommost carbon. So if we're looking at any sugar at the bottom, we have basically the carbon that's furthest away from the carbonyl that's not on the end. One that's like still like on the Fischer structures right here. If we have an OH on the right side, it's D. If we have an OH on the left side, it's L. So D, L. Cool. And D and L are mirror images of one another. But again, it's important to note that R and D and S and L are not precisely the same thing. Okay, cool. Epimers. So epimers are diastereomers that differ at a single asymmetric stereocenter. We have here and here. These structures are exactly the same, except in one of these we have an OH on the right side, and in one of these we have an OH on the left side, right? And they differ from just a mirror reflection in enantiomers because all of the stereocenters are inverted here. For this, all of them but one are inverted. Cool. And we could have a C3 epimer, we could have a C4 epimer, not a C4 epimer for these two structures, just because we only have four carbons. But for, five carbon, six carbon containing sugars, we could have, C2, C3, C4 epimers. Okay, epimerization. So there's epimerization generally occurs with carbs in basic solutions. So what will happen is first we'll abstract a proton that is alpha to a carbonyl. It's important that we're abstracting that's the hydrogen that's alpha just because that's the most acidic proton, right? After that, we'll get a double bond. These electrons will kick up here. Then, once we get this double bond, you'll see here that this position no longer is 3D, right? Since we don't have four different things connected to it, it's no longer a stereocenter. But then when the electrons come down, we grab a hydrogen. We could add the hydrogen either on this side or we could add it on this side, right? Because when we put a double bond, there are no sides. So it's very possible during epimerization we could just get a completely trivial reaction where we just add the H back on this side, OH on this side, and we get D-glucose. But we can also get D-mannose. So from this enolate ion, we can either go to here or we can go to here. Okay. Diol rearrangement. So you saw here that this was just to switch an H and an OH, effectively, right? Diol of rearrangements are to move a carbonyl from here to here. You can also use them to move it from here to here. These reactions are completely reversible, which means we can go from an aldehyde to a ketone or a ketone to an aldehyde. So it'll start off approximately the same way. The only difference is instead of the electrons coming down and grabbing the hydrogen here, they'll grab a hydrogen here and then we'll attack here. and then go through that exact process, right? So it's very similar to the concept of a tetrahedral intermediate in that we'll first attack, we'll form something, then we'll protonate the stuff that we want to keep on, deprotonate the stuff that we want to remove, electrons come down, kicks off. Cool. Reactions for reduction of carbohydrates. NABH4 is generally the reagent that you'll see when we do reductions with respect to carbs. I know you had to learn a lot of reagents for reduction in the previous chapters, but NABH4 is, pretty much the main one that we use as an H minus source. So being an H minus source, it would react exactly how you'd expect. Backside attack comes here, kicks up. Cool. That's it. And just recall that we form both of the C2 epimers because this does not have any stereo 3D orientation, right? So we could either add the H on this side or we could add it on this side. Cool. Controlling alditol configuration using an aldose. So an alditol is basically when we have C2, CH2OH on both sides, right? So this is something called an alditol. So only one compound is formed because an sp2 carbon isn't an asymmetric center when the hydrogen attacks, right? So when we attach the hydrogen here, we're forming an asymmetric center, right? But we're not doing that here because we already have one hydrogen. So we're just adding another one, which means we just have two of the same compound connected to a carbon, which means that we don't have an asymmetric center. Okay, oxidation of carbohydrates. So there's acidic and basic condition oxidations. There's harsh and mild condition reagents. Both Br2 and HNO3 only oxidize aldoses. So just keep that in mind. We can't do this on ketoses. But anyway, basically what's happening is all we're doing is we're seeing this structure, we're adding an O here. Seeing the structure, we're adding an O here. The main difference between them is HNO3 will form an aldaric acid, which means that the top and the bottom gets oxidized. However, with Br2 in acidic conditions, we only oxidize the top. So we only go from an aldehyde to a carboxylic acid. We don't go from a alcohol all the way to a carboxylic acid like we do if we use harsh conditions. So when we want to use basic conditions, we use something called Tollens reagent, and this reagent is pretty important. We'll talk a little bit more later on about why it is, what it's used for, but it basically forms something called an aldonic acid, which is when you have a carboxylic acid on the top, CH2OH on the bottom. And what's happening is it's going through an enediol rearrangement. So it could form the OH on this side or on this side. Um, and you know, it's important to note that AgNH3OH minus will oxidize aldoses and ketoses. But if you want to oxidize a ketose, you have to go through an enediol first. So what I said might have been confusing. If you start with an aldehyde, you'll go directly to an aldonic acid. If you start with a ketose, you'll have to go through an enediol to move the carbonyl O up here, and then you can go to an aldonic acid. Synthesis of carbohydrates. Let me move myself here. Okay, Kiliani-Fisher and Wall degradation. So these two are the main synthesis reactions for carbs. One of them will add a carbon and one of them will subtract a carbon, right? So the way that we add a carbon is by using cyanide because we have a carbon in this compound and we saw in A and a little bit in B that this is one of the methods that we use to extend the carbon chain. So we'll attack here. We'll kick up these lone pairs. That'll be protonated. Cool. I didn't show the protonation steps here, but it's relatively self-explanatory to see like how that would happen, right? Okay. So from here, we could have added the OHs on either sides. So when we add the CN here, like the OH could have been here or it could have been here, because again, this is not currently a stereocenter and then it becomes a stereocenter. We use Lindlar's catalyst to reduce this from a C double N to basically an imine. And after that, we use HCl to make it an OH. From there, we can, remove this hydrogen and make it an aldehyde, aldose. Cool. Okay, wall degradation. It's not precisely the opposite of Kiliani-Fisher. So what do? We add this reagent NH2OH. So this is basically just imine formation, trace acid, cool. So we replace the carbonyl O with NH2OH, cool. From there, we use AC2O at 100 degrees Celsius. So what does this do? So acylated oxide will replace all of the OH groups with OAC. Like it's not just this one. Um, and then what will happen is we'll remove a hydrogen and we'll get the CN group here. HO minus plus H2O, we'll deprotonate here, we'll kick off a CN. So you saw earlier that we add a CN. Here we kick off a CN. So again, it's not the exact opposite, but it's kind of like there's some similarities, right? Fisher proof. So this was trying to match glucose to its structures. So in a Kiliani-Fisher synthesis, these are the three reagents, right? Um, and there's a lot of things that we can do to try to figure out what structure we started with, right? So let's say we start with arabinose and we go to glucose and mannose. So these belong to a C2 epimer pair, right? So whenever we add something with Kiliani-Fisher, we get two compounds, right? We get two compounds here because we add it either here or we add it here. So with that, based on what we start with, you could kind of think like, okay, let me see like let's say I started with just not this here. Like let's say I like this was not existent, right? I just have OH, OH, HH, and I add something to it, right? So if I add something to it and it is suddenly optically active, then I know I added the OH on this side, right? And if it's not optically active, then I know I added the OH on this side. So there's a lot of logic and deductions that you can go through to try to figure out, what structure you started with. Nitric acid oxidation. You could see here that I don't have any achirality, right? Like let's say I had all the OHs on this side though, and I go through a nitric acid oxidation. So because of that, like if I had all the OHs on this side, I would now have a plane of symmetry. So it would be achiral, right? And I think you see that like right here, right? If we had this structure here and we go through HNO3 with heat, we make an aldaric acid, which is just basically carboxylic acid top and bottom. We now have a plane of symmetry. So this gives us insight into the fact that we now know where the OHs are and the H's are, or at the very least, we have two things to choose from, right? Because either all the OHs have to be here, or we have to have an OH, 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 or OH, 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 right? So there's still a lot of different choices we could choose from. Like we don't have a fully chosen structure after that. But there's a lot of steps that we can take to figure it out from there, right? Let's say we were trying to determine whether it was all OHs here. We could do a wall degradation. We could remove this and see if there's still a plane polar or there's still a plane of symmetry. And if there is, then okay, we know all the OHs were here. If there wasn't, which there won't be in this case, right? Because if we move this here, there's no longer going to be a plane of symmetry. So those are just some of the small samplings of what we can use to figure out the difference between um, uh, different sugars. This is called the Kiliani proof or the Kiliani-Fisher proof. Um, this is what was used to figure out the structure of glucose way back when. And I'm not really going to go through the specifics associated with how you'd go about very precisely doing this. But I think that it warrants a lot of practice. I think that this is one of the things that people ask about the most within this chapter. It's one of the main concepts. So I would take the time to kind of go through the different reactions and try to come up on your with on try to come up with on your own how you might go about differentiating one sugar from another, what reagents to use, what would it reveal, chirality, achirality. At the center of all of it is just, we go from chiral to achiral molecules using Kiliani-Fisher, using wall degradation, using methods to turn this and this into the same thing, this and this into different things. Yeah. All right, acetal review. So acetals are something that we covered last quarter. Hemiacetal is when we have just an OR and an OH. Acetal is when we have OR and OR. The mechanism is just classic tetrahedral carbonyl addition reaction. We attach the carbonyl, we kick this up, we deprotonate the stuff that we want to keep on, we protonate the stuff we want to remove, and we could see at this point how like this is technically a stable structure. The reactivity modes are similar to this, but we need to use excess CH3OH to install two OR groups. All right, hemiacetals with carbohydrates. So there's something called an anomeric carbon, right? So what is an anomeric carbon? So The difference between this and this is just OH here is down and OH here is up. So this is the anomeric carbon, the position at which we have an OH down or we have an OH up. We name them slightly differently. This structure is called a Haworth production. It's a little bit hard to explain, but basically we take this structure and we rotate it onto its side. So it starts like this, right? And then we rotate it this way. And with that, we see the carbonyl O here, we see the OH down, we see the OH up here, we see this OH down, we see this OH up here. And when we get cyclization, like this is the open chain form. When we cyclize into this structure, what happens is this OH at the end attacks here, we kick up here, and since this started not as a stereocenter and ends as a stereocenter, we have an orientation factor, right? And that's the anomeric thing. Okay, cool. Ring formation of aldoses. If an aldose can form a five or six membered ring, it will predominantly exist in the cyclic form, right? So in reality, this open chain form has 0.02% in equilibrium, 64%, 36%, alpha versus beta structures. And we'll go through more specifically why we have 36% in the alpha conformation and 64% in beta conformation later on. Okay. Six-membered rings are called pyranose. Five-membered rings are called furanose. It's supposed to be because these structures look similar. Honestly, I think this is a little bit of a reach, but this is convention and this is why you name it the way you name it, right? So this is galactose. Alpha means down, beta is up. So we have alpha D galactose. If we want to be more precise, we can label it as alpha D galactopyranose. Cool. Alpha D xylose, alpha D xylofuranose. Cool. Ring formation for ketoses. So for ketoses, we could plausibly form two different types, right? We can form a five-member or a six-membered ring, which is why it's a little bit important to give an extra information here, specifically for ketoses, right? Because you can see for here, it didn't really matter as much, but it does really matter when you're talking about ketosis, when you're talking about six-membered rings, when you're talking about the potential of carbs to form either five or six-membered rings. Okay, cool. All right. Pyranose, six-membered ring, form predominates in a monosaccharide. Furanose predominates in polysaccharides. This is just saying that if you have a single sugar forming for the Pyranose, sorry, if you have a six-carbon ketose and you're forming a ring structure, if you just have one of them, a monosaccharide, it'll form a Pyranose. If you have multiple, at least greater than 10, the way that the ring structure and the electronics work out is such that you favor a Furanose structure. Cool. Chair conformers. So there's a lot of different ways to write the same structure, right? So the primary alcohol is always going to be in the equatorial position. So you assign cis and trans for the rest of the OH groups based off of that. Beta D glucose has more groups in equatorial position, which makes it more stable and abundant in nature, right? So we talked about how this was 60 something percent and this was 30 something percent. It just has to do with the chair configurations, right? We see here that every single OH group is in equatorial. And this is why D-glucose is so prevalent, why you hear about it so much, and why it's so important, because it's the most stable one. It's one of the only configurations of carbs where you could have all of the OHs in an equatorial position, right? If alcohols on left of the Fisher projection, C's 2, 3, and 4 point upward on chair conformations and Haworth projections. If alcohols are on the right of Fisher projections, they'll point downwards on chair conformers of Haworth projections. So this is just saying like this is down, so this will be down. If this was up, then this would be up, right? Alpha, alpha, beta, beta. So just keep in mind, beta means up, alpha means down. Down, up. Cool. Example of a mirror image structure. Okay, glycosides. So glycosides are basically you have a hemiacetal, right? We make it an acetal, and then we have a glycosidic bond. So this OH basically becomes an OR group. So we go from a just an OH, a free hanging hydroxy group, to an OR, an ethoxy group, a methoxy group, right? So that's pretty much it, honestly. It's important to know that there's no tetrahedral intermediate that's possible though. So this is the reaction mechanism of what will happen. It's gonna be acid catalyzed. So first we protonate this, then this lone pair comes down and kicks off this OH2. So we're actually not installing two groups in here, interestingly enough. We're actually removing this. So it's slightly different than what you would expect, right? But then after that, we have this group come here, we attack here, we kick this up because now this has a plus charge on it. We deprotonate and we have this. Major is here. Major is the one that's pointing down. It's alpha. The one that's pointing up is beta. And if you recall from earlier, you can see that the one major from earlier was actually the beta D-glucose, right? Let's see where it was. Right, beta D-glucose, alpha D-glucose. So it's interesting to note that when we make the glycosides, the one that's major is the one that's pointing down. And that has to do with an effect that we haven't talked about yet, but we'll get into in a second, right? But let's just analyze this name a little bit. Okay, ethyl corresponds with this group, right? Alpha, position of the anomeric carbon. If it's up, it's beta. If it's down, it's alpha. Gluco just corresponds with glucose, D-glucose. Pyranoside. Pyranose is six-membered ring. Side means glycoside. Cool. Okay. The anomeric effect, right? So, generally when we talk about equatorial versus axial, we prefer to have all of our groups on an equatorial position. But that is not precisely true when it comes to sugars. We have something called the anomeric effect, which actually turns out to be such that oftentimes the sterically stable structure is not the most predominant structure, right? So if we saw here the major structure being beta, its sterics are favored and it has favorable solvents, but for minor alpha, we get something called the anomeric effect that's actually favored here. Um, so if we look at the difference between equatorial and axial here, we see a 5.4 to 1 here for equatorial, which makes sense, right? Because we would assume that equatorial is so much better than axial. But when we take into account the anomeric effect, it's actually only 2 to 1. And suddenly it's beta to alpha. Okay. So what's happening here? Basically, this has to do with orbital effects. So in anomeric positioning, when it's down like this, we have an O directly adjacent to it, right? And we have stability by orbital overlap. Here we don't have this because these don't overlap. So it's basically an effect of overlapping sigma orbitals to help stabilize the anomeric position. And oftentimes you'll find out that this is actually very relevant and an important factor in determining which structure of carbs is more stable. Okay, cool. This is something called Tollens test. So Tollens test was something that was used much earlier on to differentiate between reducing and non-reducing sugars. All a non-reducing sugar means is that we don't have a free OH. We don't have anything to reduce. We don't have any hydrogen to remove here. So with Tollens test, we have Tollens reagent here, and we can make an OH group here. So reducing sugar, open chain sugars, so aldehydes, hemiacetals, or hemiacetals of the ketose version. So basically anything that has a free OH group here. Tollens test will say that non-reducing sugars, glycosides, acetals can't be oxidized, which makes sense, right? We can't do anything to OR. So you look at the aldehyde position of the oxygen. Maltose is an acetal plus hemiacetal, therefore it's a reducing sugar. Sucrose has acetal bonding, therefore it's non-reducing sugar. Starch is a polymer with 300 to 600 acetals and one hemiacetal, so it's considered non-reducing. Even though the hemiacetal is technically reducing, there's just so many more sugars that are non-reducing in this polymer chain that's considered to be like a non-reducing sugar overall. And again, I think that wraps it up for the content and concepts associated with carbohydrates. There will be a lot of carbs that you need to memorize, and you will have to practice a lot with the Kiliani-Fisher proof and determining the stereostructures of unknown aldoses and unknown hexoses, as you'll come to see. But yeah, that wraps it up for now.